This is C4, section 19, differential equations. We're on page 47 of the C4 notes booklet. As usual, this is a video, so if you need to pause to take notes, please do so. It's not a lesson where I would normally give you time to write things down. Now, differential equations, some examples. So a first order differential equation is one that has dy dx in it. So simply dy dx plus cos y equals sine x is an example of a first order differential equation. So a differential equation is an equation with dy dx in it. A second order differential equation, it goes up to d2y over dx squared. So for example, d2y dx squared plus 8y squared dy dx plus 8xy equals 16x is a very complicated second order differential equation. Now that's just to describe basically what they are. Finding what y is equal to is the process of solving a differential equation. And we will learn how to do some of these type. If you want to develop this further, there are more techniques used to solve differential equations in the further pure modules. So, starting fairly straightforwardly, if we've got dy dx equals something in terms of x, we just integrate both sides to get y equals. So in this case, dy dx integrated with respect to x becomes y, integrate cos x, and we get sine x plus c. And this is what we call a general equation, because the c, we don't know what the c is, we haven't got any information to be able to work it out. So there's basically an infinite set of possible solutions corresponding to the different values of c. Getting more complicated, we can solve some differential equations by the process called the separation of variables. So in these cases, we have dy dx equals a function of x times a function of y. Now what we can do is we can divide through by the function of y. So 1 over g of y times the y by dx equals f of x. Then if we integrate both sides with respect to x, we get the integral of 1 over g of y to y dx equals the integral of the f of x dx. Now on the left hand side, the dx's can cancel. I mean, what's actually happening is much more complicated than that, but the visual effect is of the dx's cancelling. So we end up with the left hand side is integrated with respect to y, and it's completely in terms of y, and the right hand side is integrated with respect to x and is completely in terms of x. And that's what we call the separation of variables, to allow you to solve differential equations of this form. Some examples. I mentioned the idea of a general solution in example 1, so where we have a constant of integration, we won't be finding out what the plus c is. In a particular solution, which we'll do later, we'll be given information to be able to work out those missing unknowns. Right, so here we've got dy dx equals 2x plus 1 times y. So we've got a function of x times a function of y. So first of all, we divide by the y1 to take it over to the left hand side. So 1 over y dy dx equals 2x plus 1. And then we can use the process of separating variables. If we integrate both sides with respect to x, we'll get the integral of 1 over y dy equals the integral of 2x plus 1 dx. So we can then integrate those sides because we can integrate those particular functions. So 1 over y integrates to ln y, 2x plus 1 integrates to 2x squared over 2, so x squared, and 1 integrates to x. Now when it comes to the constant of integration, we can put it on either of the sides. So we're integrating both sides at once, we only really need to put a plus c at the end of the right hand side, or the left hand side if you prefer. Now some questions may ask you to rewrite this as y equals, so what we do to undo the ln, we do e to the power of both sides, so y equals e to the x squared plus x plus c. We can tidy up the right hand side a bit. So laws of indices means that we can break up the e to the power, so e to the c times e to the x squared plus x. Well, because c is a constant, e to the power of c is a constant, so we can just replace that with a single letter. We often use a, or y0 in this case, because it will usually correspond to the value of y when x is 0. So we get, in the end, a general solution, we get y equals a times e to the x squared plus x. And that's the first example, well, of these sort. And then with boundary conditions, we can find particular solutions. In this case, the boundary solution is that we're told that when x equals 1, y equals 4. That will allow us to lock in our constant to a particular value. So we'll need various steps for this one. So again, we've got a complicated function. We divide by the function in y. So 1 over y minus 2 to y by dx equals minus 4 over 2x plus 1. Integrate both sides with respect to x and we'll get the integral of 1 over y minus 2 dy equals the integral of minus 4 over 2x plus 1 dx. Now when integrating fractions, the ideal would be that the top is the differential at the bottom, so that when we integrate we get ln at the bottom, or the denominator, to use more mathematically precise language. So left hand side, differentiate the bottom, we get 1, that is our numerator, so it integrates to ln of y minus 2. The right hand side, the denominator differentiates to 2, but we've got minus 4, so we need a bit of correcting. We want 2 there, but 2 times minus 2 is the minus 4 that's actually there, so you put a minus 2 at the front. And so when we integrate, we get minus 2 ln of the denominator 2x plus 1. Now in these cases where all your functions are in terms of ln, instead of putting plus c, we can put plus lnk, so that we can use the laws of logarithms to simplify things. So on the left hand side, we're going to leave as it is. For the right hand side, we can take the minus 2 in as a power. Using the laws of logarithms, and then we're adding those so we can times those together. So ln of y minus 2 equals ln of k times 2x plus 1 to the minus 2. Now the reason we're doing this, of course, is that we want to rearrange to y equals f of x. So we need to rearrange our equation to y equals. We're moving up to the bottom there, so I'm going to move that upwards. So to undo, we can take the ln's away, so we get y minus 2 equals k times 2x plus 1 to the minus 2. So to get the y equals, we add the 2 across. But if we were looking for the general solution, we'd be done. But we're not looking for the general solution. We're looking at a particular solution when x equals 1 and y equals 4. So sticking in the values, 4 equals k times 2 times 1 plus 1 to minus 2 plus 2. So 4 equals 3 to the minus 2 is k over 9 plus 2. Take 2 off both sides. 2 equals k over 9. Times both sides by 9, k is equal to 18. So we get our constant integration, stick it back into the y equals to the final answer. So y equals 18 2x plus 1 to the power of minus 2 plus 2. And that gives us our particular solution for the particular case where x equals 1, when x equals 1, y is equal to 4. Right, those are differential equations where you're given the equation. Sometimes you might get a question where you have to work it out from a scenario instead. So you're told in words, and you have to form the equation and then solve it. So the rate of increase of a population P with respect to time mathematically is dP over dt, and it's proportional to the size of the population. So it's some constant, which I'm going to call K, times P. And we're given some boundary conditions. When t equals 0, population's 8. When t equals 1, it's 56. We're on the size of the population when t equals 2. So what we've got is a separation of variables case. We're using p and t instead of y and x. So we divide by the p. We get 1 over p, the p by the t equals k. So we can use our constant as being our function in terms of t. Integrate both sides with respect to t, we get the integral of 1 over p, the p equals the integral of k, the t. Integrating, left hand side integrates to ln of p, the right hand side to kt plus c, where c is our constant of integration. We want p equals, so e to the power of both sides, we'll get rid of the ln, so p equals e to the kt plus c. Similar trick to what we did before. We can split that up into e to the c times e to the kt. Or we can replace e to the c with a single constant letter, because if c is a constant, e to the c is also a constant. So again, I'm going to call it A, though some people would call it P0 in this case. So we've got our general solution. Now we're told when t equals 0, the population was equal to 8. So 8 equals A times e to the k times 0. Well, e to the k times 0 is just 1, so we get A is equal to 8. So from the first bit of information, we're able to work out one of the missing constants, which is Ra. So we now know that P is equal to 8 e to the kt. From our second bit of information, we're told that when t equals 1, P equals 56. So sticking that into our new equation, 56 equals 8e to the k times 1, which is k. Divide both sides by 8. Seven equals e to the k. Ln of both sides to undo the e to the power. We get k equals ln of 7. Therefore our equation is now P equals 8e to the t ln 7. Now the k we wrote before the t, but we write the ln 7 after the t to make it clearer what we're doing. So we're not mixing up with ln 7 times t with ln of 7t, which is something different. Now to finish off, we want to develop the value of the population when t equals 2, so we simply need to stick t equals 2 into our formula. So p equals 8e to the 2 ln 7, which actually gives us a nice number. It is possible to do this without a calculator. In this case I am going to, it gives us 392. I'll show you also how to do it without a calculator. It's unnecessary in terms of a calculator exam such as C4. But using laws of logarithms, 2 goes into as a power. So it's ln of 7 squared. So it's equal to 8e to the ln of 49. E and ln are inverses, so we end up with 8 times 49. And using whatever calculation methods, for example, times an 8 by 50 and then subtracting 8, we get 392. And this concludes this section.